All right, our last section for this semester, we're going to take a look at something called optimization. And if you remember back in Chapter 3, what we were working with is applications of derivatives. So this is a final application of derivatives that pulls together a lot of things that we've done along the way, but in a little bit of a unique way of doing it. So to start with, some guidelines for optimization. Optimization often has something for you to make a visual sketch of. It's not always, but often it does. So making a sketch is a good thing to do. Identify either like cognizantly just in your brain or maybe written down if it's helpful, things that you know and the things that you need to find. Write any applicable equations. That's definitely something you're going to write down. We need to figure out what it is we're trying to optimize and then write that equation in terms of only one variable. Sometimes it's already written that way. Sometimes it's not, and we have to go back and actually change something along the way. And then if you'll remember what we were doing really in Chapter 3, at least a lot of, is we were trying to find maximums and minimums of things. That's what optimization is. Optimization is optimizing something, and optimizing it means it's making it the best it can be. That's usually talking about something the biggest that can be or the smallest it can be. So if you think about things from like a business perspective, right, you're trying to optimize the profit, right, a maximum profit for an organization. Or perhaps you're trying to minimize the costs. That's a minimum for something that you're looking for. So looking for maximums and minimums, that's a business kind of perspective. We can do this from a physical perspective too, right? So like if you're talking about maximizing the area of a home with minimizing the cost of building it, things like that. So we can do those too. And then on step 5, we're using calculus to find extrema, which means we're taking derivatives, setting them equal to 0 and solving. Or potentially setting them equal to where they do not exist and solving. All right, so we're going to look at one first that is an area problem. I like to bring this one up because you've seen a variation of this probably in a college algebra course solved from a different perspective. And it's a good reminder that there's more than one way to solve things. And so this is showing you how you can use calculus to do the same kinds of problems. And then we'll do an example that's not one you would have seen before too. So we have a 3-sided fence that we're going to build along a section of river. The enclosed area needs to equal 1,800 square feet. And then we want to find the minimum perimeter and dimensions of the corresponding enclosure. So why would we want to find the minimum dimensions? Well, because the fence is what we're actually putting down, and it's going to cost us money. So we're really finding a minimum in terms of the supplies of what we're trying to find, right? That's why we're trying to find the minimum in this situation. All right, so to start with, a picture. So we've got a river, and we're going to make a rectangular enclosure along the side of the river. So it's going to look something like this. So it's worth noting that we only have 3 sides that we're fencing in, and the last one's the side of a river. Some variations of this you sometimes see is that this is along the side of an existing structure, like a house or a fence already. So there's no need to put another fence along a fence that already exists, right? You're building into what's already there. This one's along a river. Now there's some things that you know about rectangles. You know that the rectangle's width is the same on the top and the bottom. Let me use X because that's what I've got on my paper. It's the same on the top and the bottom because it's a rectangle. Opposite sides are equal, right? It's possible that this third side's also the same, but we don't know that for sure, so we'll give it a different name just in case it's not. There's nothing special about the variables I'm using. They're just matching my notes, so if you were using something different, you get to the end, it'll all be just fine, not a problem. There's some things that we're told, though. So we're told the situation about the rectangle. What's another piece of information we're told in this particular description? Yeah, the area is the 1,800 square feet. So what is an area of the shape that we're working with? What's that formula? Length times width. And the length and the width are x and y. So the area here is length times width, or x times y, and it's 1,800. And I'll put the square feet here. If you left them off, it'd be okay for now. Okay, so that's good information. That's a piece of information that we know. We still don't know x and y. That's what we're actually trying to find, right? It says down here, find the corresponding dimensions, find the minimum perimeter and the dimensions. So I need to figure out what x and the y are. But it's actually wanting me to optimize, that is to minimize perimeter here, right? So I need an equation for perimeter, but it needs to be the perimeter of this picture, not just the perimeter of any arbitrary shape, right? So what's the perimeter of the shape that I'm working with right here?
2x plus y.
Right. It's 2x plus y. Now, in a general equation for a rectangle, it'd be 2x plus 2y, right? But this one doesn't have that other y side, so it's just not there. So make sure you're working with the perimeter formulas or whatever your formulas you are for the actual shape as it's described. Okay, so this is what I'm trying to minimize, right? This right here is my minimization. And what we learned in chapter, minimize, here we go. What we learned in chapter 3 is to minimize things, we take derivatives, set them equal to 0, and solve. And that's great, except that if you take a look at this, I can't take the derivative as it stands right now because I have two variables, okay? Now you learned back in section 2.6 that there's related rates. That's how things are changing. So we did have a way of taking derivatives when there's more than one variable, right? We did that in the last section. But that's not what's happening here. Things aren't changing, right? There's no time that's changing the dimensions of the shape that I'm working with. So it doesn't apply in the same way here. I really need this to have one variable. And in fact, if you take a look back at the direction sets, that's what it said. We need to get this in terms of one variable. So I need this equation down here to have either x or y in it, but not both. Does everybody understand my goal at the point where I am right now? I need to eliminate one of these. But if you take a look back at the equation before, we have an equation before that has an x and a y in it as well. Right? So how is that helpful? Well, one of the methods that you learned in an algebra course or a college algebra course or a pre-calc course or something along the way is that when you have two equations, which we do, and you have two unknowns, which we do, substitution is a good way of eliminating one of those variables. Substitution and elimination are the two ways that you tend to look at from an algebra perspective. So if I take the one that's in the equation, or so the equation that's in the box, and I solve it for x or y, and it doesn't matter, you guys can pick for me, then we're going to use that to eliminate the variable in the other equation. So do you want to solve for x or for y? It's a tough decision. X will work. Okay, so if we solve this for x, what will x equal?
1800 square feet.
By y, right? It's 1800 over y. I'll leave my dimensions off at this point, and we'll put them back on at the end too. So down here in my equation for perimeter, I'm just going to call it P now. I've got the 2, and then I've got the x, which I've just eliminated by making it 1800 over y. And then I have plus my y. And if I simplify just a tiny bit, I have this as 3600. And I'm going to move my y up, y to the negative 1 plus y. And this is the equation that I now need to find the minimum value for. I need to optimize. So we take a derivative. So what is the derivative of 3600 y to the negative first? Yeah, a couple people echoing in. Yeah, that's right. Good. And then what's the derivative of y? It would be dy dt if we were working with time as a changing variable, but that's not what we're doing here. It's just with respect to x, so it would just be 1. Yeah, there's no time variable changing like there was in 2.6. Okay, is that all right? So then again, from an optimization standpoint, right, finding maximums and minimums, we take the derivative. We set it either equal to 0 or to does not exist. So if you take a look at this one, I think I have space on another sheet. Yep, we'll move this equation to the next slide and keep working. We're going to set this equal to either 0 or does not exist. I'm going to take one step in between here and rewrite this 3600 over y squared plus 1. And I want this to either equal 0 or to equal does not exist. So in order to get this to equal 0 or to equal does not exist, I need to combine the pieces that are on the right-hand side together, at least for the does not exist one. That's how I'm going to have to handle it. And since that's an option, and it's a possibility too, because I've got a denominator, right? There is something y can't be. Y can't be 0, right? So I'm going to combine these two fraction pieces together. So if I get a common denominator, this ends up being negative 3600 plus y squared over y squared. It either equals 0 or it does not exist. Okay, so far so good? You know where it doesn't exist, because we just said it. Where does it not exist? Sorry, at y equal 0, right? How can I find out where it's equal to 0? What does that equate to? We're finding the extrema, but we find the extrema potentially when it's equal to 0 or when it's equal to doesn't exist. So concretely, what's my next step to find out where this is equal to 0? Yeah, the numerator is equal to 0. So if the numerator of a fraction is equal to 0, the whole fraction's 0, right? And if the denominator is equal to 0, that's the doesn't exist part that we've already done. So I really need my numerator to equal 0. So you can separate these on sides of an equation if you wish. This is y squared equals 3600. You can square root. If you want to put the plus or minus on, you can. But remember the picture over here for what y is. It's the side of the length of fence. It's not negative. So I don't really need the negative part of that I would get. So I can actually just use the positive part. What's the square root of 3600? 60. Okay, so we have two values. We have 60 and we have 0. And if you take a look really quick, we know it's not negative. We already mentioned that. But it's also not 0, right? What happens if y is 0 here? We would have no area, right? We just have a long piece of fence extending straight out from the river. Doubled. It would be a silly looking fence, wouldn't it? Yeah, so it wouldn't make any sense. So it really can't be 0. In fact, if you take a look at values that make sense, and that's actually part of this description too, it says write any, let me see where it was. Determine the maximum and minimum allowable values, if any. We didn't really talk about them, but to find those, it means looking at it and saying what seems reasonable. Well, y can't be 0. That's not possible. And you could say, well, the absolute biggest not possible reasonable thing we could do is let y equal the entire length of the fence too, right? That wouldn't work either. So we have our values for y is that y would in fact need to be bigger than 0. And then it's got a cap on it for it to be making sense, and we can take a look at that later. But at the very least, we know y is greater than 0. So when we're looking at finding out whether or not this value, 60, really achieves the minimizing of the perimeter, which is what our goal is, we're trying to take a look at a sign chart. Do you guys remember sign charts? Yep. And this sign chart really does have a capping end. Like it can't be below 0. So I can put the 0 on the end as a breaking point, or you can probably put a parenthesis there. It would make a little bit more sense. And I need to pick values both before 60 and after 60. So we get to choose. It doesn't really matter what we choose. 1's a nice value that we often would pick, and maybe you pick 70 or something like that. I don't know. So we pick a couple of values. And we're plugging this into the derivative. And either of these versions will work of our derivative, whichever one you like better. And what we want to know is we want to know the sign. Do I get a positive when I plug the value in, or do I get a negative? So let's start with the number 1. If I put the number 1 in for y squared, or for y, and so I've got negative 3600 over 1 squared plus 1, do I have a positive or do I have a negative? I get a negative. Yeah, this is negative. What if I put in like 70? You might want to grab your calculator. If you put in negative 3600, divide by 70 squared, add your 1. Do we get a positive or do we get a negative? You get a positive. Yes, you do. So what that means is the graph is decreasing, right? Negative on a derivative means it's going down, and then it's increasing. So what does that tell you happens at 60? It's a minimum. This step right here is the step that most people forget if they mess this problem up at some point, but they do most of it right. They often forget to verify that they really did find a minimum. They get to the point of y equals 60 and they're like, good to go, I found my answer, right? But they didn't really verify that it met the conditions it was supposed to meet. So put yourself a note there that says, remember, got to do a sign chart to verify this piece. Now we haven't quite, answered the question asked, but we've done most of the work for it at this point. We've found what y is. What else do we need to find? What x is? That's one of them. So x is 1800 divided by y. Right? So 1800 divided by the y is 60. So what is 1800 divided by 60? 30. So now I have a value for x and I have a value for y. But it's not exactly what I was asked for. What did it ask me to find? Perimeter and dimensions. So dimensions means that the values are the x and the y, but I need units associated with them too. So let's do perimeter first. So the perimeter is 2 times x, which was 30, plus the y, which was 60. So what's my total perimeter? 120 what? Feet. Right? 120 feet is my perimeter. And then my dimensions are the x and the y with the corresponding units. So and it doesn't matter the order, it's 60 feet by 30 feet. Or you could say 30 feet by 60 feet. So pay attention to the question that's being asked. Don't stop shy of actually answering the pieces you're asked for or forgetting the units on them, right? Feet's different than meters, right? They are. They're different. We need to make sure we're reporting back the answer in the units that we're given. All right, any questions on that one? Okay, the next two are going to feel less like college algebra. This didn't feel like college algebra in the solving, but the setup did. The next two don't quite have that same feel. All right, this is like the stereotypical question that's always asked in this section of material for any calculus professor ever. So if you've taken calculus class before, you've probably seen a version of this question. It's a very, very classic question. We have a box, and it's Christmas time, so I should have brought a box to actually show you that this is how the box is constructed, but we've got a box. The box is to be built by taking a 6 by 10 inch sheet of cardboard and cutting x-inch squares out of each corner, and then folding up the sides. Find the value of x that maximizes the volume of the box. Okay, so put in your mind like a t-shirt box, or we're not talking about the Amazon box that you take off the top, it's not like that kind of a box. A shoe box, okay? And imagine flattening it, okay? The shoebox, bottom of the shoebox box, and flattening it. So you'd have to cut down the corners, right? And then you'd flatten it out. That's the image they're describing that we're starting with the corners cut out. So our picture, as we're drawing this, looks something like this. And what we're doing is we're cutting the corners and we're folding them. So I'm going to do some dotted lines to represent the folds. I think a little thicker would work better. So these are the fold lines along the edges. And we have to cut out the corners completely. So if you can imagine taking each of these corners, and cutting them out, right? So these corners are actually going to be the cuts, these red pieces. And then we fold along the dotted lines. It would fold up on the edges and it would make a box. A topless box, but it would make a box. Okay, everybody good so far? Okay, it tells us how big the cardboard is to start. It's 6 inches by 10 inches. So the way that I've drawn it, my 6 inches would have to be along the top. And the 10 inches would have to be along the side. And then it tells us that we're cutting x-inch squares out of each corner. So this and this are both x. And I'm not going to write it on every single corner, but every corner has those x dimensions. I'll write it on one more corner so that we can talk about the top of the box. So what we want is we want to maximize the volume of the box, right? How much it can hold. So that's where we're going to start. My first question is, how do you find the volume of a box? The volume is length times width times height. Well, the length and the width must have something to do with the 6 and the 10. That was the length and the width of the original cardboard piece of paper. The height has to do with it being folded up. So the height's probably the easiest one to look at and say, oh, look, if I fold the corners of this box up, right? So I take my paper and I fold the corners of the box up, and the fold was cutting out these corners that were X's. How tall is my box? X, right? So the height is the easy one to see. The length and the width are a little trickier. Let's talk about the width, because I marked it on the top part first, 6 inches. It started out with a width of 6 inches, but then I've cut out some of that width. In fact, the width that we're talking about is actually this piece right here. So what would the width be, given that I started with 6 inches across? 6 minus 2x, right? I subtract an x off from the left, I subtract an x off from the right. So my width is 6 minus 2x. Hang on, let me shift this over a little bit. Using that same idea, here's my length. What would the length be of the folded box? Somebody's saying it. 10 minus 2x, right. So I have 10 minus 2x for my length, right here. I have 6 minus 2x for my width, and now I have an x for my height. And that's actually friendlier in some regards than our last equation, because I already have an equation that has only one variable in it, don't I? I don't have to eliminate any variables. Or you could say I'm eliminating my variables as I discover what L, W, and H each are based on my picture. You could say I'm doing that. All right. So taking a look at this, I'm supposed to maximize this thing. Before I do, let's actually talk about what makes sense for x, because x is the only variable in my equation now. X can't be negative. I can't cut a negative corner out, right? So 0 is sort of the beginning part of what x can be. X has to be something bigger than 0. What is the absolute most that it can't go beyond? Think about your picture. What's that? 10 and 6 are the numbers we're looking at, but it's not 10 or 6. 5 and 3. So where did you get 5 and 3?
2 times 5 is 10, and minus 10 is 0.
Okay, so I'm going to use your 3 one as an example because it's smaller.
Okay.
So if you take a look at the top, if you were to cut 3 inches in from the top, you'd be cutting the box in half. You would not have a box, right? So my value for x can't be more than 3 because I'd take 3 off from the left, 3 off from the right, and there'd be no box. So the cap here is 3. That's going to be really important for this one because we're going to have some values show up that aren't going to make any sense in the terms of the context of the particular problem. So we want to make sure we're thinking about what makes sense in the problem. All right, so using this, we want to take a derivative. And if you really want to use like product rules and so forth to take the derivative, you could. But I think it probably just makes sense to multiply this out and then take the derivative on this one. So that's what I'm going to suggest. So we're going to FOIL out the first piece, and then we'll multiply through by the x. So I have 60, let's see, this is negative 12, and this is negative 20. So negative 32x. And then I have positive 4x squared. All that's times x. So I end up with 60x minus 32x squared plus 4x cubed. I'm running out of space a little bit as I'm running into my 10 inches. So let me shift it. This is volume. Right? That's the volume equation just multiplied out. But I want to maximize my volume. So the way I maximize things is I take derivatives and then I set them equal to either 0 or does not exist. Now this one doesn't have a denominator, right? It's just a polynomial. So there won't be a place it doesn't exist. But there will be a place potentially where it's equal to 0. So we're going to take derivatives. What's the derivative of 60x? How about the derivative of 32x squared? Negative 64x. And then 4x cubed. 12x squared. Yeah. Okay, so far so good? So I was working with one of my children last night on fraction simplification, and I feel like this is the same sort of thing. At this point, could you try and factor it? Well, you could, but because there's common factors in all the numbers, it's going to make it harder to work with. So it's a really good idea at this point to recognize, hey, look, they all divide by something. Let's divide them all by that same something. What number will they all divide by? 4. So let's divide them all by 4, because it'll make the problem easier to work with. So if I divide everything by 4, 60 divided by 4 is 15. How about 64? 16 and 12, 3x squared. And if it bothers you that they're sort of written in backwards order, just flip them around. I have 3x squared minus 16x plus 15 equals 0. Generally, at this point, we would look and we would try and factor. I'm going to spoil all your fun right now and just let you know it's not going to factor. A lot of application problems, like real-world stuff, they don't. Right? That's kind of normal. So after you've looked at this, whatever problem you're at, and if you do in fact decide it does not factor, what would be the next option that you could try? There's 2 more options. What are they? Quadratic formula. That's the one we're going to do. If you really felt so inclined, you could also do completing the square. That's the other option. So we're going to do quadratic formula. So to do the quadratic formula, if you'll remember, it's x equals, and I'll write it all down just as a reminder, negative b plus or minus the square root of b squared minus 4ac all over 2a. And a, b, and c are now presently in order. This one's a, this one's b, and this one's c. So, b is negative 16, so this b at the beginning here, the opposite will be positive 16. Plus or minus the square root of b squared, so 16 squared. Technically it's negative 16 squared. It's going to eliminate itself, so you don't have to write it, but I will. Minus 4, a was 3, and c is 15. All over to a, or 2 times 3. Now this is going to give you 2 answers because there's a plus or a minus, right? So we're going to simplify a little bit of this as we go. It's not going to be a perfect, beautiful value coming out. I know it's not going to because it didn't factor, right? So that's not an unexpected thing at this point. I don't expect that this is going to look nice. 16, is that 256 when I square it? Yes. I have 256 minus 4 times 3 times 15. It's 180 over 6. So aside from finding an approximation, there are ways we potentially could simplify this, but it's not going to help. I'm going to have to get an approximation at some point. So this is plenty cleaned up enough. I don't need to look for like dividing common factors out or simplifying the 76 so that part of it comes out of the radical and part of it stays there. I don't need to do any of that. I'm going to get a decimal approximation, so at this point it might as well just do it, right? So we're going to do 16, and I'll do the plus one first. So 16 plus the square root of 76 divided by 6. So if I do the addition one, I get 4 point, we'll go with 2 decimals for now, 1, 2. And if I do the same thing, but I do subtraction, I have 1.21. So these are my 2 options. But I need to verify which one works, or maybe both of them, right? And I also need to verify that it really does give me the maximum, not a minimum, that I'm looking for. So I've got a sign chart. But a moment ago, when we set up our sign chart, we talked, or not when we set up our sign chart, but when we set up our problem, we talked about things that x can and can't be. X is bounded between 0 and 3 within the context of the problem. So as I'm taking a look at this sign chart, that 4.12, it doesn't go anywhere because it's outside of the interval that makes sense for the problem. And that's really why we need to make sure that we're paying attention to that, is so that we don't end up trying to use pieces of information that just don't work for our context. 1.21 is in between. So we'll try a number before, I'll use 1. We'll try a number after, and I'll use 2. And we're putting it into the derivative. And if you wish, you're welcome to use the version that's on the screen at the very top where I've identified the A, B, and C. Or you can use the one that has the 4's multiplied through back over here before I divided them out. That would be fine too. So you could use this version of it if you wish. So you're going to put in the number 1, and then you're going to put in the number 2. So when I put in the number 1, I actually get a positive, and if I put in the number 2, I get a negative. Positive means it's increasing. Negative means it's decreasing. What does that mean happens at 1.21? I have a max. And that's what I was looking for, right? It is. I was looking for a max. So my x value, cutting the corners, is at about 1.21 inches that I need to cut out of each corner. That's what I'm looking for, but what did the question actually ask me to find? I need to be careful. It did. It said, find the value of x that maximizes the volume of the box. So my answer really is x equals 1.21 inches. But I could have been asked to find the maximum volume of the box, right? I could have. That would have been another question that I could have been posed with. So just pay attention to the question that you're being asked to make sure you're answering what's being asked. Any questions on that one? Okay, we're going to try one more. This one's, again, a different style of question. So we're going to find the point on a curve, y equal x squared. You know what that curve looks like. The point that is the closest to the point 0, 1 in the plane. So we're going to start with a picture. This is a picture of a parabola, right? Looks something like this. We could probably draw it on a grid and get a little bit better picture, but this is really good enough. The point 0, 1, so this is my graph y equal x squared. The point 0, 1 would be right here. Okay? So we could talk about, well, what happens if I go straight out to the left and to the right? If I go straight down, maybe I need to go at an angle, but you can definitely tell me that the answer is not going to be something over here, right? That is not the closest point to the point on the graph at 0, 1. So whatever my answer is, reasonably speaking, it's going to be somewhere down here. Agreed? It has to be somewhere over there for it to make any sense. So those are the expectations that I'm setting forth as I look for this particular problem. And in fact, we know that we could get something at least 1 away. We can definitely get a value. That 0, 0 value is exactly 1 away. So whatever this distance is, it can't be more than 1, because I can for sure get 1 away and make that work. Okay? All right, so what are we looking for? We're looking for something related to distance. Do you remember the distance formula? Okay. Do you remember, there's 3 formulas that are equivalent. The distance formula, the Pythagorean theorem, and an equation for a circle. Okay, so the distance formula's version of that formula looks like x1 minus x2 squared plus y1 minus y2 squared. That's the distance formula. And just to verify with you what I'm talking about, the Pythagorean theorem is a squared plus b squared equals c squared. And if you're letting your a and your b be ordered pairs with the x, not the a and the b, but if you're looking at locations in the xy plane and you're doing the distance between these, Can you see how you can go from that to my distance formula? And if you think about the equation of the circle, which we haven't talked about in class, so it's fine, but x minus h squared plus y minus k squared equals r squared. Do you see all the pieces look the same too? Yeah, these are all just different applications of the same type of a formula. So the distance formula itself is the one that we're going to start with here. That's the version of it that we're going to work with. So there is a point that we're trying to find the distance to. It's 0, 1. So it doesn't necessarily matter which of those you use, that is the x1 or the x2, but we need one of them, I'll just use the second ones, to be the ordered pair 0, 1. So that's going to be one of the things that I'm going to write in. The square root's going to stay. I'll put in the other pieces as we go. But x is 0 and y is 1. So that's part of the equation set up immediately because that's one of the points. The other point is an arbitrary point that I don't know. So let me just plot something. Let's say it's right here. This point right here is what I'm calling x1, y1. Okay? Or if we want to, since we've already eliminated these, you can just call it, actually let's do that. We can call it just x and y. So I could put an x here, right? X minus 0 and y minus 1. I could put those in, but that's not especially helpful directly because I need an equation that has one variable, and that would still give me 2. So if I put that in right here, it's not that it's wrong, it's just that it's not finished. I need to figure out how I can rewrite either x or y in terms of the other variable. And there's something on your screen that tells you exactly how you can do it. Daniel's nodding. Do you see it, Daniel? What do you see? It's the equation, right? The relationship between x and y is the equation that we're working with. So that's what I'm going to use to eliminate, in this case, the y value. The y value is x squared. So instead of having this written like this, I can rewrite this. I know x minus 0 is x, but we're just going to write it one more time. And I have x squared minus 1 squared. Because that's what y is. Y is x squared. So there's nothing really special about this equation, y equal x squared. I could give you this exact same problem, and I could just give you a different equation, and we could do the same thing, right? I can give you a different point. It doesn't have to be the point 0, 1. We could do the same thing. Okay, so we're going to simplify this now, clean things up. Obviously, like I mentioned, x minus 0 is x, so this is just x squared. Please, please, please remember that you don't just get to square each component when you square a quantity like that. You have to FOIL. You'll kind of giggle, but people do it all the time. And I think that probably you have all done it at one point too, because you just get going quick and you forget. But this means x squared minus 1 times x squared minus 1. So as we're working through this, we have to FOIL this out. I will leave this kind of all combined together for the moment. So I have x squared. The inner and the outer are both, I'm sorry, x to the 4th, I meant to say. X to the 4th. The inner and the outer are both negative x squareds. So I have negative 2x squared. And then at the end, I have plus 1. All right, so we're going to clean this up. Obviously, the x to the 4th can't combine with anything, but the x squared and the negative 2x squareds can. That gives me negative x squared, right? And then I have plus 1. This is the most simplified version of the derivative formula that I'm going to be able to accomplish. I didn't mean derivative formula, distance formula that I'm going to be able to accomplish. But remember, optimization. This whole section is about finding optimal values. How do I find the optimal value, in this case the minimum value for my distance? Well, I do the same thing every time. I take the derivative, and then I set it either equal to 0 or it does not exist. So that's where I am now. I need to take the derivative. Let me make one more comment over here too. The x value itself, so we talked about the fact that, let me change colors, that this point right here is exactly 1 distance away, right? It's 1 away down here. It's actually the same thing if I go over here. This is a distance 1 away because the ordered pair 1, 1 is on my curve, right? So if I go straight to the left and the right, I've got 1 unit away. I can do it to the left side as well. So if you wish, we can go over to here. What I'm trying to point out in showing you this is that this right here is the range of values that make sense for x. Anything bigger than positive 1 or smaller than negative 1 is further away than 1. It's not going to be a value that I'm looking for. So my x value is somewhere in between negative 1 and 1. Those are the values I'm looking for. And it probably shouldn't surprise you for me to say this either, but there should be two values because the graph is symmetric, right? Whatever value I find over here that's my red dot, there's going to be an equal value over here that's the same distance away from the 0, 1, right? So I'm going to get two answers for this because of the symmetry that's going on here. Okay, back to my problem. We need a derivative. So we want the derivative. As we take the derivative, this is equivalent to having this equal to a power of 1/2. So let me rewrite that in there that way. So I have my 1/2. I rewrite the inside, x to the 4th minus x squared plus 1 to the negative 1/2. And then I need the derivative of the inside. So that's 4x cubed minus 2x. Okay, so far so good. I can simplify this, clean it up a little bit by putting this square root now on bottom, x to the 4th minus x squared plus 1. There is a 2 down here with it, but the 4x cubed minus 2x squared, you might notice there is a 2 that can factor out of all of those, right? So this is going to be a 2 now, and that'll be a 1. I'm pasting. So now I have 2x cubed minus x squared over the square root of x to the 4th minus x squared plus 1. And I want this to either equal 0 or equal does not exist. How do I get a fraction to equal 0? The numerator is 0, right? So getting the fraction equal 0 means having the numerator, that's the 2x cubed minus x squared, equal to 0. And then the denominator equaling 0 would be where it does not exist. And while I know that there's a square root in my denominator, it would have to actually be a 0 underneath the square root for that to happen. Yes?
Was it x squared or just x? Because when you took the derivative...
Did I copy it wrong? I might have. You're right, it was. There should be just a 2x, not a 2x squared. Thank you. Let's try to move over here. Take that squared off. So sorry. Okay. Everything else look okay? Okay. And this one equal to 0. All right. So this piece actually, the x to the 4th minus the x squared plus 1, it will never equal 0. If you attempt to solve that with a quadratic formula or factoring, you'll find that none of it actually gives you any values. What happens if you do the quadratic formula on it actually is that you'll get some imaginary values. That's what will happen. And so once you get that negative underneath the radical, you'll know that there's nothing that will actually equal 0. What that means is it just doesn't cross the x-axis. There aren't any places for 0. So this one's not going to happen. The first one, though, does. I can factor an x out. That gives me 2x squared minus 1 equals 0. So obviously here x is equal to 0. And then 2x squared minus 1 equal to 0 gives me 2x squared equal to 1. X squared is 1/2. And then the x value is positive or negative the square root of 1/2. And if you rationalize that, that's square root 2 over 2. Which, for those of you who remember some unit circle stuff, that should seem like a familiar value, square root 2 over 2. If you don't remember, it doesn't matter, but it is a familiar value from the unit circle. So there are 3 values right here that I would potentially put on my sign chart, right? My sign chart has a capacity to go from -1 to 1. 0, of course, is in between those. If you check the square root 2 over 2, it's also in between those. It's about 0.7. So we have a negative square root 2 over 2, and we have a positive square root 2 over 2. And I know we're running short on time, so let me just tell you what happens when we put those values the in-betweens of those values then. This one's negative, positive, negative, and positive. So negative and positive, positive, negative, negative, positive, like this. So here is a minimum. Remember, I'm trying to minimize distance, and here is a minimum as well. So I have two minimum values. I have, and I think it says the points, right? Find the points. It says the point. There's two of them. These are with x values. So when I have square root 2 over 2, and I have negative square root 2 over 2, those are the x values. And then to find the corresponding y values, I have to plug them back into the original equation. Well, the original equation said y equals x squared. And when I square each of these, I actually get 1/2. And the reason that this is a familiar place from your unit circle perspective is because this is actually a 45-degree angle. So this is coming down from here at a 45-degree angle, or you can say that it's coming up from the y-axis that way from a 45-degree angle. So that's why that square root 2 over 2 is coming through. So we have 2 points that minimized the distance.